Welcome to 3SP-105 339 Motor Relay Module. In this module, we'll cover these topics: hardware, actual values, quick setup, system setup, protection, and controls. The common functions of 3 series introduced in the previous modules won't be repeated. The concepts in FMPR 109 will be highly recommended to watch FMPR 109 module before watching this 339 relay module. In the hardware portion, we will introduce front panel LEDs and RTD inputs. In the 3SP-101 hardware module, we used 350 feeder relay as example to explain the front panel LEDs. Now we're going to introduce 339 motor relay specific LEDs: stopped, starting, running, hot RTD, lockout, start, inhibit. For the common LEDs like in service, trouble, trip, alarm, pickup, maintenance, please refer to 101 hardware module. Stopped LED turns on when motor status is stopped. This LED color is programmable with default to red. Starting LED turns on when motor status is starting. This LED color is programmable with default to orange. Running LED turns on when motor status is running. This LED color is programmable with default to green. Hot RTD LED turns on to orange when either a RTD alarm or trip has been activated. Lockout LED turns on to red when the following elements are activated: thermal overload, short circuit, mechanical jam, ground fault. Start inhibit turns on to red when the start inhibit element is activated. 339 relay has 2 methods of supporting RTD inputs. As an option, CAN bus-based RMIO modules can be installed on the 339, which can monitor up to 12 RTDs. Alternatively, input-output option R can be selected from the order code. This option provides 3 internal RTDs and 4 outputs, 1 form A and 3 form C. 339 relay does not support both internal RTDs and RMIO RTDs simultaneously. The RTD type supported is 100 ohm platinum. Each of these may be configured to have a trip temperature as well as an alarm temperature used for motor, stator, and bearing temperature protection. All 3 RTDs share a common return and shield terminal. In the actual value part, we'll talk 339 specific values: motor status, learned data, and data logger. Motor status can be found under actual values, status, and motor status. There are 5 stages for motor status: tripped, stopped, starting, running, and overload. The motor status is tripped following any protection trip operation or lockout. The status can be reset when the protection trips and the lockout have cleared. When the motor status is stopped, detection of the phase current above FLA changes the status to starting. Running status following starting when the current drops below FLA. Running status continues as long as phase current greater than 5% of CT is detected. To accommodate application where current does not rise above the thermal overload pickup setting on start, running status is also declared when the contact inputs indicate the motor is online. From running status, if the current is above FLA, then the motor status change into overload. When phase current falls below 5% of CT, status changes to stopped. To accommodate application where motor idle current is less than 5% CT, a further requirement to change status to stopped is that the contact inputs do not indicate the motor is online. 339 relay measures and records individual data records from actual motor operation. The latest individual data records can be viewed using Learned Data feature under Records. The data when input cumulatively to Learned Data records can be used to evaluate change trends over time. Note that learned values are calculated even when this feature are turned off. Each of the learned feature discussed below should not be used until 5 successful motor starts and stops have occurred. Learned data includes these parameters: acceleration time, starting current, starting thermal capacity used, last acceleration time, last starting current, last starting thermal capacity used, learned average load, and average runtime. Data logger is used to sample and records up to 10 actual values at selectable intervals. Data logger can be run with continuous mode enabled, which will continuously record sample until stopped by the user, or with continuous mode disabled, which will trigger the data logger once without overwriting previous data. To view the data logger, go to Records and click Data Logger. And then click Launch Viewer. So the data logger values can be viewed in the data logger screen, and this data can be saved into a COM_treat file by go to the menu, choose Save As. So you will see the extension name .cfg for the COM_treat file. In the Quick Setup screen, user can set up these most often used parameters for the relay status to be ready and the nominal frequency 60 Hz or 50 Hz. For the system setup, the CT primary and ground CT types can be selected, as well as the CT ground CT primary. For the motor parameters, the motor FLA can be defined. The switching device can be choose breaker or contactor, and also the definition for the 52A and B switch. And for the VT sensing, VT type can be selected as Y or delta connection, and also the secondary voltage and VT ratio. And the protection element can be configured on the quick setup is the thermal model, short circuit function, mechanical jam, undercurrent, ground trip, and phase under voltage. In the system setup section, we'll talk about motor specific set points, motor switching device, and VFD, variable frequency drive. Motor setup is under set points system setup motor. In the motor setup, the nominal current FLA can be specified for the full load amp. Also set up for the motor rated voltage
and rated power. When two-speed feature is enabled, the 339 provides the second independent short circuit and undercurrent element for high speed and adjusts the thermal overload curve and acceleration time as per the high-speed motor characteristic. The setting available for the high-speed CT primary, high-speed FLA, high-speed rated power, and high-speed switch and low-speed switch. Switching device is under System Setup, Switching Device. 339 relays support two-type switching device, breaker and contactors. The switching from breaker to contactor will affect the settings of output relays under Inputs Outputs, the breaker controls under Controls, and the breaker failures under Controls. Also the breaker monitors under Maintenance. When the switching device is changed from the breaker to contactor, so all these relevant settings either disappeared or being changed. When the switching device selected as breakers, the assignable output relay will be output relay 4 to 6. When switching device is changed to contactor, the assignable output relay will be output relay 5 to 6. Relay 4 will be used to control the contactor coil. When start button is pressed, contactor coil will be energized and sealed in by the CC contact when start button is released. VFD, variable frequency drive, function must be enabled in order to ensure proper performance of the 339 relay for motor applications with VFD. There are two types VFD motor applications. First is motor starts and runs through the VFD. Second is motor starts through VFD but runs through the bypass switch. In motor applications where the VFD can be bypassed, status of the bypass switch must be configured as a selected input under setpoint VFD bypass switch. When bypass switch is open, VFD bypassed operand is not asserted. Frequency will be calculated from phase A current. Frequency element will be inhibited if phase A current is below 10% of nominal current. When bypass switch is closed, VFD bypassed operand is asserted. All the function is disabled. Then the frequency source is switched from current to voltage. All protection elements and metering work as normal.
In the protection section, we'll introduce these specific motor protection elements. Motor thermal model, short circuit, mechanical jam, load increase alarm, undercurrent and under power, current unbalance, ground fault, phase reversal, acceleration time, RTD protection.
The primary protection function of 339 motor relay is motor thermal model. Thermal model protection integrates stator and rotor heating into one module. While the motor's equivalent current is greater than the thermal overload current, then the TCU thermal capacity register is updated every 3 cycles. When motor is in overload, the motor's temperature and the thermal capacity used will rising, and when the thermal capacity used reached 100%, a trip will occur. When starting thermal protection is enabled, start protection is used to determine the time to trip values while the motor status is starting using this formula. Locked rotor current is a steady state motor current while the rotor locked, when supplied from a source at rated voltage and frequency. The thermal overload curve have a standard curve. By using these standard overload curve equations, all can be set as the flex curve. And the curve can be shifted by using the curve multiplier. The pickup setting defines the current level at which motor is considered to be overloaded. Normally, the thermal overload pickup setting is set slightly above the motor service factor. When the unbalanced key factor is enabled, it sets the degree of unbalanced biasing using the thermal overload curve. 0 will disable this unbalance function. RTD bias will be enabled when RTD software options is selected in the order code, and RTD will be also used in the thermal capacity calculation. For the detailed information about the thermal model, please review FMPR 109 motor protection. In the thermal model of 339, it includes standard curve, start protection, unbalanced bias, and RTD bias. If short circuit is enabled, a trip or alarm occurs once the magnitude of any phase current exceeds the setting of short circuit pickup for the time specified in the delay. Care must be taken when turning on this feature. If the interrupting device, contactor, or circuit breaker is not rated to break the fault current, the function of this feature should not be programmed as trip. Alternatively, this feature may be programmed as alarm or latched alarm and assigned to auxiliary relay connected to upstream device, which is capable of breaking the fault current. Mechanical jam is specially designed to operate for running load jams. After a motor has started and reached the running state, a trip or alarm occurs should the magnitude of any phase current exceed the setting mechanical jam pickup for the period of time specified in the mechanical jam delay. The mechanical jam level should be set higher than the motor loading during normal operation, but lower than the motor stall level. Normally, the delay is set to the minimum time delay or set so that no nuisance trip occur during momentary load fluctuation. Load increase alarm is used to alarm abnormal load increases that may indicate problem with the process. An alarm is enabled only after the acceleration stage is complete and the motor has entered running stage. In the load increase alarm logic diagram, the input average current compared with pickup setting. After the delay time, we'll assert load increase operand. Same principle works for short circuit and mechanical jam. The differences are the pickup levels and time delays. When motor is in running state, an alarm will occur if the magnitude of any phase current falls below the undercurrent alarm pickup level for the time specified by the undercurrent alarm delay. Furthermore, a trip will occur if the magnitude of any phase current falls below the undercurrent pickup levels and for the time delay of the trip delay. The alarm and trip pickup levels should be set lower than the lowest motor loading during normal operation. The undercurrent element is active only when the motor is running and is blocked upon the initiation of motor start for a period of time defined by the setting block undercurrent on start. This block may be used to allow pumps to build up head before the undercurrent element trips or alarms. Underpower element is response to total three-phase real power measured from the phase current voltage. Underpower may be used to detect loss of load conditions. Loss of load condition will not always cause a significant loss of current. Power is a more accurate representation of loading and may be used for more sensitive detection of load loss or pump cavitation. When the motor is in the running state, if the magnitude of three-phase real power falls below pickup level for the period time specified by the delay, the pickup level should be based on the motor MNR, motor nameplate rated power, and should be set lower than the lowest motor loading during normal operations. In the logic diagram of undercurrent, each individual phase current drops below the pickup will assert undercurrent pickup operand, while in underpower, only three-phase power below the underpower pickup level will assert underpower pickup operand. For 339 relay, unbalance is defined as a ratio of negative sequence to positive sequence current, or multiply I average over FLA when I average is less than FLA. This desensitizing is necessary to prevent nuisance alarms when motor is lightly loaded. When setting the pickup levels, note that 1% voltage unbalance typically translates into 6% current unbalance. To prevent nuisance trip or alarm, pickup level should not be set too low to avoid nuisance trip or alarm. For example, if supply voltage is normally unbalanced up to 2%, then current unbalance seen by a typical motor is 12%. In this case, set the current unbalance alarm pickup to 15% and the current unbalance trip pickup to 20%. This way, we can prevent nuisance tripping. 5 or 10 seconds delay is reasonable. Unbalanced trip curve can be set definite time and inverse time. For the inverse time curve setting, the curve of the unbalanced current is defined as this equation. From the logic diagram, we can review the Fortescue equations to calculate positive negative sequence current and unbalance value. A trip or alarm occurs once unbalance level equals or exceeds the set pickup for the set period of time. If the unbalance level exceeds 40% or when I average is 25% FLA and the current in any phase is less than the cutoff current, the motor is considered to be single phasing and the trip occurs within 2 seconds. Single-phasing protection is disabled if the unbalanced trip feature is turned off. Before setup ground fault protection, the CT type should be pre-selected. This option can be either a core-balanced CT, CBCT current used for detection with small current magnitude, or is a force CT input with either 1 amp or 5 amp second current rating. On solid grounded system where the fault current may be quite large, the 1 amp or 5 amp secondary ground CT should be used for either zero sequence or residual ground sensing. Core balanced CT, CBCT is used for sensitive ground fault detection, including ground faults due to resistive leakage. The CBCT has a ratio of 50 to 0.025, which makes it ideal for the detection of ground fault primary current even in the range of 0.5 amps. To use the CBCT 50 to 0.25 input, select this option under ground fault type. The pickup levels of the ground alarm and trip is a multiple of the CT or amps depends on the ground CT type selected. The delay has the on run used when motor is in running condition or on start when the motor is starting condition. In the logic node of ground fault, we can see the pickup is related to the ground CT type. The delay is related to the motor status. Phase reversal can be used to detect the phase rotation of three-phase voltage. This setting is related to the system rotation setup under power system. From the logic diagram, when phase voltage VAB, VBC, and VCA are greater than 50% of motor rated voltage, if the phase rotation of three-phase voltage is not the same as the supplied rotation set point, and there's no fuse failures, either an alarm or trip and a start inhibit will occur within 100 milliseconds. Acceleration. When enabled, acceleration protection will trip if the motor starts in the starting state and does not reach the running state by the set acceleration time. In the logic diagram, the acceleration time start timing when motor is in starting status and wait for acceleration time times out. For two-speed motor application, separate time settings are provided for acceleration time from stopped to low speed, for acceleration from stopped to high speed, and for acceleration from low speed to high speed. In the hardware part, we introduced there are two types of RTD, remote RTD RMIO, and internal RTDs. Each RTD may also be configured as being application type of stator, bearing, ambient, or other. Each RTD can be set for alarm and trip. The alarm temperature is normally set slightly above the normal running temperature. The trip temperature is normally set at insulation level. Please review FMPR 109 for the insulation classes. Trip voting is provided for extra security in the event of RTD malfunction. If enabled, second RTD must also exceed the trip temperature of the RTD being checked before a trip will be issued.
In the control part, we'll cover these specific motor controls: welded contactor, start inhibit, Emergency restart. Reset.
Breaker failures or welded contactor functions are related to the setting of the switching devices. These functions monitors phase current after trip command from protection element is initiated or logic operand programmed as breaker failures, external initiate, welded external initiate is asserted. If any phase current above the set current level after the programmed time delay, a breaker failures will be declared when breaker was chosen in switching device, or welded contactor will be declared when contactor was chosen as the switching device. The time delay should be set slightly longer than the breaker or contactor operating time. 339 has included two programmable timers for the breaker failures and welded contactor functions. Timer 1 starts counting down once the trip condition is recognized or the programmed logic operand is asserted. Timer delay 2 does not begin counting down until the timer 1 has expired and one of the phase current is above the setting breaker failures welded current. Thermal start inhibit function is provided to inhibit starting of a motor if there is insufficient thermal capacity available for a successful start. The motor start inhibit logic algorithm is defined by the thermal inhibit set point. If this set point is set to 0, start inhibited until thermal capacity used decays to a level of 15%. If this set point is set greater than 0, start inhibited while the available thermal capacity is less than the learned thermal capacity used at start. Start per hour inhibit. This element defines the number of starts attempted allowed in any 60 minutes interval. Once the set number of starts has occurred in the last 60 minutes, start controls are inhibited until the oldest start contributing to the inhibit is more than 60 minutes old. Time between starts. This function enforces a settable minimum time duration between two successive start attempts. A time delay is initiated with every start attempt, and a restart is not allowed until the specified interval have elapsed. Restart inhibit feature may be used to ensure that a certain amount of time passes between the time a motor is stopped and the restarting of that motor. Emergency restart is used for situation where continuation of a process driven by the motor is more important than protecting the relay itself. Closing these contact inputs will discharge thermal capacity used register to 0. And also reset the start hour block counter, reset the time between the start block timer, and reset all trips and alarms so that a hot motor may be restarted. Therefore, while the emergency restart contact input terminal are shorted, the trip output relay will remain in its normal non-trip state. The lockout reset and reset under 339 relay. Lockout reset input reset any lockouts as well as any trips or latched alarms provided that the condition that caused lockout alarm trip is no longer present. If there is a lockout time pending, the start inhibit output will not reset until the lockout time has expired. Reset allows a push button or other devices located external to the relay to perform the same function as the reset push button on the relay faceplate. Closing this contact input reset any trips or latched alarms provided that the condition that caused the alarm or trip is no longer present. Lockouts and start inhibit are also reset if the lockout reset setting is off.
Now let's recap what we learned in this module. 339 is a cost-effective and flexible protection and control device for motors. It has all the benefits of 3 series relays. Its front panel LED will show the different status of motor in different colors. That information can also be viewed under Vista software. 339 can be ordered with or without RTD inputs. There are 2 types of RTD inputs, internal and external, which cannot be supported simultaneously. 339 learned data can record motor starting current, thermal capacity used, and acceleration time after 5 successful starts. When VFD is used, its bypass switch needs to be configured, and it may affect the frequency protection element. Motor thermal model includes negative sequence bias and RTD bias. And don't forget to review FMPR 109 about the concept of thermal model and insulation classes. Unbalanced calculation is divided for normal load and light load conditions to avoid nuisance trip. Fortescue equations are used in unbalanced calculation. Underpower is provided in addition to undercurrent protection to provide more sensitive to the loss of load protection. 2 types of ground CT are provided for the ground fault protection. RTD protection can be used for bearing and stator with RTD volting function to avoid faulty RTD maloperation. 2 types of switching devices are available, breaker and contactor, which corresponding to breaker failures and welded contactor. To protect the motor, start inhibit is provided, but it can be defeated by the emergency restart when the process is more important than the motor. And that concludes this 3SP-105 339 motor relay module.